Before I move on to the next project in this Art of Electronics series, I do want to kind of close out the integrator and some of the issues that I found that differ from the author's findings. You may recall, if you watched my last video, that the author suggests that you try grounding the input to the integrator and watching how quickly the output integrates the small input errors. In other words, the errors like the offset voltage and the effect of the offset input current. Well, I have been trying to figure out why I'm getting a different result, and frankly, I have come to the conclusion that I'm not going to get a really different result. I'll tell you some of the things I have tried. What happens in my case, and you may notice that up there the meter, I've had this circuit sitting for well over an hour with the input grounded, and it just doesn't seem, the output right now is 103 millivolts, and I'll show you in a minute, relate that to the DC gain and so on. But what I've tried, let me show you first the breadboard. One of the things that occurred to me is that the feedback resistor might be, that the effective resistance might be lower than the 10 meg. I'll show you the schematic again if you don't recall that from the original video. But so I changed it to a 22 meg. I also used a different capacitor because it occurred to me that the capacitor I had might be leaky for some reason, and that's why that it doesn't accumulate enough, doesn't accumulate charge over a period of time. So I used a completely different kind of capacitor, and I checked them both on a very reliable Sencor capacitance leakage meter, and they don't leak. These are 630 volt capacitors being used in a 30 volt circuit or a 20 volt circuit. So so what were the possibilities? Well, I considered the possibility that the breadboard itself might be leaky, and I'll show you why I rejected that here in just a second. So let's take a look at the original circuit. Over here. And you may recall the original circuit had a 10 meg feedback resistor to give the integrator a DC gain of 10 million to 100,000, or a gain of 100. So, as I said, I had changed this to a 22 meg to see if that made any difference, and also to test another hypothesis I had, which was that maybe there was some leakage, other leakage on the circuit that was causing it not to accumulate charge. So anyway, these are the values that I got in terms of the output voltage. With the 10 meg resistor in, at 9:36 last night, I was getting 52 millivolts with the input grounded. After 30 minutes, I was getting 51.3, and after another 30 minutes, I was getting 51.2. This morning, I've been trying it with the 22 meg resistor. It started out at 105 and 20 minutes later had drifted down to 104.7, and 20 minutes after that down to 104.3. And let me tell you why this is some importance. One, you notice that these numbers are exactly twice these numbers, or within approximately twice. And if you recall, I said that I changed the feedback resistor to a, get down out of that shadow, that feedback resistor, well, there's my meter going off. The one of the things is that this drifts so little that the meter that I have times out before it drifts enough to take a reading. So I wind up having to turn the meter off. I'll do that right now, and then turn it back on 20 or 30 minutes later. So the original circuit had a DC gain of 10 million over 100,000. Or 100. With the 22 meg in, it has a gain of 200, and that is one reason that these numbers are effectively twice as much. But that also tells you something as well. It tells you that the gain of this stage, the DC gain, is linear to the feedback resistor. And what that means is that if there is any leakage, it is in the order of hundreds of megohms. It's very, very high, because had I changed this, say, to a 22 and I didn't get twice as much, that would imply that there might be some additional leakage through this, from the output to the input of this op-amp. And by the way, I'm using LM411s here, or LF411s, which is exactly the amplifier that the author used. So the bottom line is, I've come to the conclusion that this circuit, for some reason, it can't be that I just happened to luck out with one op-amp, because as I pointed out in previous videos, I tried several of those Motorola op-amps, the 4304s or 3403s, and I forget the numbers. At any rate, the other op-amp, I tried several of those. And now I have completely rebuilt the circuit using LF411s. Let me show you once again the breadboard and point those out to you. Here is the input buffer. This is the integrator. And this is the output buffer. Once again, as I say, completely different capacitor, completely different resistor, and the resistor twice as much. Everything points to the fact that this particular circuit does not drift, or I should say, does not accumulate much output error due to the input offsets. So I had hoped at some point to perhaps work on a project having to do with input offsets. It is a real problem, and I had hoped to compare maybe non-chopper stabilized with chopper stabilized and that kind of thing. But I think I've decided not to go there, at least not trying to use an integrator to do that. We'll do that another way. At any rate, I'm at a stopping point on this, so I think it might be time for me to move on to the next project, which I think is probably, well, I won't say because I might do something else in the meantime, but move on to another project in the art of electronics.